All right, welcome. Today, we are diving deep, pulling back the curtain on one of the most, fundamental ideas in all of computing, the process. It's the secret sauce, right? The thing that lets your computer do a million things at once. So, what exactly is in that sauce? Let's get into it.
I mean, think about it. You've been there, right? You're listening to music, typing up a document, you've got like a dozen browser tabs open, and you just stop and wonder, how? How is all of this happening at the same time without, the whole thing just crashing and burning? Well, the answer to that little magic trick is something called a process. Okay, so what is a process, really? The best way to think about it is with an analogy. A program. That's like a recipe in a cookbook. It's just a passive list of instructions, sitting there on your hard drive, not doing anything. But a process, well, that's the chef in the kitchen, actually cooking. It's that same program, but now it's in execution. It's active, it's using resources, and it's making things happen. Okay, so now that we've got a handle on what a process is, let's pop the hood and see what it's made of. What are the essential parts that make up this active, living thing inside your computer? So every single process gets its own little slice of memory, and it's usually organized into four main sections. You've got the text and data sections, that's for the code and variables, but the really dynamic parts are the heap and the stack. The stock is for temporary data for functions, and the heap, that's for memory you allocate on the fly as you need it. And here's the cool part, they actually grow towards each other. The operating system has to act like a referee to make sure they never, ever collide. So how in the world does the operating system keep track of hundreds, maybe thousands of these processes all at once? It uses this thing right here, the process control block, or PCB for short. The best way to think of it is like a process's passport or its ID card. It contains literally everything the OS needs to know about that specific process.
And what's in that passport? Well, the PCB stores the process's current state. Is it running right now, or is it waiting for something? It holds the program counter, which is just a pointer to the very next instruction, and, so critically, it saves all the CPU registers. Think of it like a bookmark for our chef from before. It's noting the exact page and the exact line number of the recipe they were on before someone interrupted them.
Just like a living thing, every single process goes through a life cycle. It's born, it lives, it does its work, and eventually it terminates. And understanding this whole journey is absolutely key to seeing how your OS manages, everything. So here are the 5 states. A process is new when it's first being created. Then it enters the ready queue, kind of like it's in a waiting room, ready for its turn. Once the scheduler picks it, boom, it's running. Its instructions are actually executing on the CPU. Now, if it needs to wait for something, like a file from your slow hard drive, it enters the waiting state. And when it's all done, it becomes terminated. Here's the most crucial point, though. At any given moment on a single CPU core, only one process can be in that running state. Just one. And that brings us right back to the multitasking magic, doesn't it? If only one process can run at a time, but you have tons of them in that ready state, how does the OS give each one a fair turn on the CPU? The mechanism that makes this all possible is called a context switch, and it is the very heartbeat of a modern operating system. It's actually a really elegant two-step dance. So the OS decides it's time to switch. Step 1, it freezes the currently running process. Let's call it P0. And it saves its entire context. The registers, the program counter, all of it, into P0's PCB. Then step 2, it pulls up the PCB for the next process in line, P1, loads its saved context into the CPU, and just like that, P1 is now running, picking up exactly where it left off. But, and this is a big but, there's a cost. This switch time is what we call pure overhead. While the switch is happening, the system isn't running your music or your word processor, it's just doing internal bookkeeping. So the whole game is to make these switches incredibly, unbelievably fast. We're talking microseconds, to maintain that perfect illusion of seamless multitasking. Okay, and here's a fun, maybe slightly spooky fact from the world of operating systems. When a process finishes, it doesn't just poof, vanish. It enters that terminated state, but its entry in the process table actually sticks around until its parent process acknowledges its death. Now, if the parent is busy, or maybe it crashed and never checks, that terminated process becomes a zombie. It's dead, but its ghost is still kind of hanging around the system.
So up until now, we've kind of treated processes as these isolated individuals, each in its own little world. But what if they need to work together? How do these separate, protected entities actually communicate and cooperate to get a larger task done?
Well, the answer is something called inter-process communication, or IPC. It's basically a whole set of mechanisms that allows processes to break through their isolation bubbles to share data and synchronize their actions. And this is absolutely crucial for everything from speeding up big computations to something as simple as copy and paste.
And there are two main ways that processes can talk to each other. First, you have shared memory. This is like giving a bunch of processes a shared whiteboard. It's incredibly fast once it's set up, because they can all just write to it and read from it directly. The other model is message passing, which is more like sending letters or text messages back and forth. It's often safer and a bit easier to implement, but it can be slower since the OS has to act as the mail carrier for every single message.
To really see why IPC is so important, let's look at a classic computer science problem, the producer-consumer problem. The idea is actually really simple. One process, the producer, creates some data, and another process, the consumer, uses that data. Just think of a web server producing a web page that your browser then has to consume. They have to be perfectly coordinated.
A really common solution uses a shared, fixed-sized buffer. So the producer adds items to this buffer, but it has to wait if the buffer is full. Meanwhile, the consumer is taking items out, but it has to wait if the buffer is empty. The absolute key to making this all work without chaos is synchronization. Without it, the consumer might try to grab an item that isn't even there yet, or the producer could accidentally overwrite data before it's been used. It's a really delicate dance.
So why did we just go through all this? Why does it matter? Well, because it directly explains your everyday experience with your computer. You know when an app seems to freeze while it's saving a huge file? It's probably in the waiting state, just stuck waiting for your hard drive. Or when your whole system gets sluggish and choppy, you might have way too many processes in the ready state, all fighting for a limited number of CPU cores. Understanding processes gives you this new lens to see what's really happening under the hood.
So we've pretty much established that processes are the fundamental building blocks of multitasking. They let your computer juggle lots of different programs. But what if a single application, a single process, needs to do multiple things at the same time? Think about your web browser. It's rendering the page while it's also downloading images in the background. What's the mechanism that allows for that level of parallelism within a single process? What's the next layer down? Well, that is a fantastic question, and it's the perfect topic for our next explainer.